welcome back. In our last video, we talked about counting techniques. And by that, we mean exploring combinations and permutations and their differences, the types of problems that we could kind of start to solve. And we did some very simple examples. In this video, we're going to spend the whole video just kind of going over, it's basically one problem, but I'm going to show you some different techniques and some different ways of looking at things to be able to set up a typical kind of probability type word problem. Okay, and this is kind of the classic light bulb problem. It turns out that there's, even in this textbook series, there have been 3 or 4 different versions of this exact problem running around, although they've changed some of the wattages and those kind of things. But for what we're doing, we're going to deal with the scenario that we have it's a collection of light bulbs, if you will. And imagine you have a box of light bulbs, and in it you have 4 40-watt bulbs. They're all numbered 1 through 4, and 6, and some 60-watt bulbs that maybe those were 5 through 9, and then 75-watt bulbs would be 10 through 15 would be the kind of the numbering. But there's this assortment of bulbs of different groups in here. But the idea is that each of these 40-watt bulbs is an independent bulb. It's not the same bulb 4 times. It's that each bulb is unique, even though it has the same rating. Okay, so what we're going to do is we're going to take all these bulbs, we're going to mix them in together in a box, gently, of course, so we don't break them. Okay, and so now we have a box with 15 bulbs of different wattages in them. Okay, and now what we're going to do is we're going to pull 3 at a time out of this. And in this, the order doesn't matter to us. We're just going to reach in, grab 3 bulbs, and look at it. So this is one of those assumptions I said in the last video that we needed to watch out for, is that we got to watch out for this order matters or order doesn't matter. All right, so the order doesn't matter tells me it's a combination problem that's going to show up. All right, so what we can do is we can start to kind of set this problem up, and I'll show you kind of how you do it with formulas, and then I'm going to show you an alternative way to be able to kind of look at those. All right. All right, so in this example, so first thing we want to do is we need to count the number of possible outcomes in the sample space. Okay, and so we said that was a combination of 3 pulls on 15. And so we're looking at, again, 15 factorial over 15 minus 3 factorial over 3 factorial. And if I do the math, it simplifies down to this 15 times 14 times 13 over 3 times 2 times 1. All right, and so the top part of this, if you'll remember, that would be my permutation of 3 on 15, and then I have this k factorial portion that showed up down here, right? Because again, the formula that we're looking at is n factorial over n minus k factorial over k factorial, and that last term was a combinatoric thing that accounted for repetition. All right, so if I do that math and I shake it out, and trust our calculator, we've got 455 ways of selecting 3 bulbs out of this set of 15. And again, this would be numbers starting to get large enough that it's not something I would want to sit there and write out every possible one, because like I say, I would probably miss one if I tried to account for them all visually. So we've got to kind of take a leap of faith and start to trust the equations that are working for us. Okay, and so we've got 415 possible sets of 3 bulbs occurring in this particular sample space. All right, so let's try some different problems, see if we can figure out the events and how we would start to set this. So the first one that we're going to do is we're going to look at the number of ways that we can select exactly, and that should be two 75-watt bulbs on that 3 bulb pull, the number of ways in which that would happen. So now, again, we're pulling 3, but I only specified that I needed exactly 2. So what that implies then is that my outcome X is the scenario where I have 2 75-watt bulbs, and then I have the one that isn't. Okay, and that, if you look at this, not 75, and I'm starting to see this not thing, so maybe that's a complement sneaking around, and we'll get to that here in a second. But some keywords the way we set this up. But this accounts for my three bulb pull, if you will, as we start to look on. All right, so what we're going to do is we're going to then look at an event X such that I'm pulling 2 bulbs from 75 out of 6 possible, because there are only 6 of the 75-watt bulbs possible. So the number of ways that I can get X then is the combination of 2 on 6. Okay, and so if I do that, 6 factorial over 6 minus 2 factorial is 4 factorial times 2 factorial. That gives me 15 ways that can happen. Okay, and so that's the number of ways of X. And again, that's a combination of 2 on 6 happening there. All right. Man, lighting's being a bear. What if I turn it off? All right. There we go. Let's try that. Okay. So then the other part of this event, so this is a compound event because we've got a simple event of 275s. The other part of this then is that I need an event Y in which I pull one that is not 75 watts. Okay, now notice that not 75 watts is going to imply that it's either a 40 or a 60. Now I don't care which one it is, so we can look at this then as being 9 possibilities of not being 75. Okay. And so we're going to look at then doing the number of ways of Y as being 1 from 75, not 75 watts from 9 possible. So we're doing a combination of 9 on 1. And so if I do that, there are 9 possible ways. A lot of times when you see a 1 on this thing, it's basically just that value of that top number because everything else cancels. All right, so that's my 9 ways. So then if we define event A as being the event where both X and Y are happening, then that becomes an intersection of these two sets. Okay, so they have 275 watts from 6 possible and at the same time 1 that's not. Okay, and so by our product rule, okay, or our multi-rule on this, it's going to be 15 for my N1. So this is like saying N1 is this guy and little n2 was this guy. My product rule says, well, when that happens, I have 15 of those events and then I have 9 of the other. It's 15 times 9. I have 135 ways that this compound event can happen, X intersect Y, or 275s and 1 not, on a 3-bulb pull. All right, so then the probability of my event A is now 135. That's my, we're doing N of A over N of S. Okay, and that's this calculation here. And so 135 over 455, we have a probability of just under 30%, 0.2967 if you do the math. All right, so that's one kind of a basic problem. Now, again, all we did there is kind of the classic brute force method where we look at, let's just use the formulas and equations and just start writing things. And, again, to me, I'm a visual person, so I like to have pictures and graphics to help me kind of reason my way through this. And so we've got another alternative way to handle these I think greatly simplifies a lot of these combination and permutation problems. And it's what we call the pool problem. Okay, and so this is my alternative way, and it's going to look a lot like a tree diagram on here. And so what I've done is I've defined my pool as being the sample space S. And so you can see it does kind of look like that tree diagram, right? That I could have, pull something from 75, 40, 50, or 40, 60, whatever the case may be. And the way that I write this is I take the total possible ways of S was 15. Okay, it was the sum of all of the bulbs in the box. Okay, and I'm going to pull out 3. And so anytime I have something being pulled out of one of these pools, that's a combination. So the combination up here then is 15 and combination of 3. Well, that is the number of ways of the sample space. Okay, and we said that that was 455 for that value. Okay, now we can go in and we can look at our pools and figure out the criteria of the events that would satisfy this. Okay, so, for us, we're pulling 3 bulbs. And so the first criteria was that I had to pull 2 out of here. So when I pulled 2 out of this, that's a combination of 2 on 6. Okay, and then at the same time, I needed 1 from the others. So that could be, and for this, it's simple enough. I could say, well, I could have a 0 out of 4 and pull the 1 out of this guy. Or I could do another event that was 2 out of the 75 and then do 1 out of the 40 and 0 out of this. Both of these events satisfy the criteria that I get exactly 2 out of this one. Okay, so you've got to account for all of the outcomes. Okay, and so if we do this, the number of ways of the events of this happening is just combination. So it's 2 on 6 and 0 on 4 and 1 on 5. Okay, and the number of ways that even happens is this equation. So you can see how the numbers in the pool start to set themselves up. 2 on 6, 0 on 4, 1 on 5, all combination equations. All right, so when I do that, we know from before that 2 on 6 is 15, 0 on 4, there's only one way I could not get a 4. Okay, and then I'm looking to pull 1 out of 5 on that, so that's times 5. So there are 75 ways that I could get this event. Okay, in which I pull my other pull is a 60-watt bulb, and I get 275. Okay, now the other event that satisfies the criteria, because again, we didn't specify that third bulb, what it could be, that we could be, a 2, a 1, and a 0, so now it's 2 on 6 and 1 on 4, and that should be a 0 on 4 there. Okay, or 0 on 5 there. And let's clean that up. 5 and 0, but 0 on 5 is still 1, so my math is still correct. Okay, and so 6 on 2, 4 on 1, 0 on 5, so 15 times 4 times 1, that gets me 60 ways. And so then all I do to get the number of ways of my event A is just add up 60 plus 75, or 135 ways, right? And so if you look, when I do that, that number is the exact same as what we saw when we did the formulas blindly on there, all right? So that's, not bad. And to me, I can kind of visualize this. Now, again, if I have a lot of other categories here and trying to make sure you don't miss any, it's still limited in how it works, but at least you can kind of visualize what's coming from where and how the equations come out of that. Okay, but I'm going to show you another way, and this trick is a binomial pattern. Okay, and it's kind of cool. And you remember in the last video I talked about that complement and kind of keeping our eyes on that equation. All right, so if I consolidate this, I could rewrite this pool problem in the following way. My sample space is still 3 out of 15, so that number doesn't change. And then I need 2 out of my 75 on this, but instead of writing 40, like I did up here, 40 and 60 separately, I'm now going to lump them all into what I call a not 75, okay? Because I don't care where they're coming from. And so if I do that, then the number of not 75 bulbs in here is 4 plus 5 is 9. And now I just know I'm pulling 1 out of that guy, okay? And it works. So that I could do, 2 on 6, 1 on 9, 15 times 9, there's the 135 again, okay? And this trick of using, because this guy is a complement of 75 watts, meaning it's not the 75 watts, it's exclusive from that's a kind of a cool trick. And this is actually a real clever trick when we get into probability distributions and even some statistics of ways of simplifying problems, is that we have some formulas that will allow us to look at this binomial guy. And by binomial, it means that we have one of two outcomes. And the two outcomes on this are it's either is 75 or it's not. Okay, whereas before I didn't have that situation. I had 75 and then the others specifically. But the math works out exactly the same way. So that's kind of a cool trick, and we'll come back to this and we'll visit that time and time again, because with binomial I can make some assumptions and my formulas become very, very quick and very, very easy to do those, even beyond the problems that we're working now. So take this word binomial and kind of file it away back in the back of your mind for a couple of lessons, and then we'll come back around to that in a big way when we get into probability distributions. Okay, all right, so that's how we're going to handle that. All right, so our second example for this then is what's the probability that all three are the same? Okay, and so again, I'm just going to jump straight to the pool problem to kind of illustrate the scenarios in which this can happen. All right, so again, sample space, 3 and 15, that part doesn't change. I'm going back to my pools of 75, 40, and 60, and I did that so that I could just basically reestablish I didn't want to do a binomial pattern on this, but I could say, well, one scenario is I have a 75 and not 75. Okay, but what we're going to do is we're going to say I'm going to pull all 3 out of 75 satisfies the criteria that all 3 are the same. I didn't say which wattage, but it's just that they were the same. Okay, and then so I have 0 out of 4 and 0 out of 5, and I put them together, 3 on 6, 0 on 4, 0 on 5, the combinations. And if I do the math, that's 20 times 1 times 1. I have 20 ways that I get all 3 75s, okay, on a 3-bulb pull. Okay, go to the second event then, is instead of pulling 75, I now pull all 3 40s, and so that's going to be 0 out of this one, and 3 out of this one, and 0 out of this one, so it's 0 on 6, and 3 on 4, and 0 on 5. The math says 1 times 4 times 1. There's only 4 ways that I get that one. And then on the last one then is that they're all coming out of the 60, and so that's 0 and 0 and 3, and so now it's 0 on 6, 0 on 4, 3 on 5, 1 times 10, and then add them up. I have 34 ways that I get all 3 are the same particular bulb. So now we just go in and we can do our probability on this. So the probability of that event B, again, number of ways of what I want. So event B over the total number of ways. We have 34 over 455 is 0.0747. Probability is a little less than 8% that I get all 3 the same. So you see, all of a sudden we're starting to ramp this thing up and we're solving a lot more complex problems. Okay. Now, what about the one of each? What you can do is you can pause the video and see if you can start to solve this thing yourself. By now you know the tricks on this, okay? So once you've paused it, pause, now unpause, we come back. So we're going to do sample space is 3 on 15. That's 455 ways again. And so the pool problem for this is then just 1 from 1 from 1. from each of the pools, right? So it's 1 on 6, 1 on 4, 1 on 5, 1 on 6, 1 on 4, 1 on 5. 6 times 5 times 4 gets me 120 ways, unique ways that can happen. So the number of ways for event C is 120, right? So then the probability of this guy is, number of ways of C over number of ways of the sample space is 120 over 455, or 0.2637. And so easy, it's just the same skill. And so these pool problems, like I say, they break down very, very nicely. And they kind of help me visualize, and they even show me how to put these formulas together. At the end of the day, all you're doing, this whole calculation right here, that's that product rule that we said back in the last video was N1 times N2 times N3. Okay, and all I'm doing for N1, N2, and N3 is I'm calculating the ways that of each of those events that can happen, and I'm chaining. Now again, there are the assumptions that we've got to be mutually exclusive, that I can't pull a bulb that is both a 40 watt and a 75 watt. That makes sense. But you do have those restrictions still in place behind the scenes. All right? Okay, so the last one then is a little bit more unique, okay? And this one's got a little bit more complex, and I kind of want to kind of illustrate this to you. The scenario is that the probability that I must pull at least 6 bulbs before I get my first 75 watt bulb. Okay, now this is a compound event, and this is kind of, the wording on this is kind of vague and not real clear on what's going on, okay? And what I'm going to point out on this one, and we hinted at this earlier, is that sometimes using the complement is easier, and I'll show you why. Okay, so what we have here is we're going to define our event D as the number of ways greater than or equal to 6 in which the first 75 watt bulb is pulled. So what it means is that my possible outcomes are that we're looking at event D as being that it takes 6 pulls to find the first 75 watt bulb, 7 pulls to find the first 75 watt bulb, 8 to find the first, 9 to find the first, and then at 10, something interesting happens, because if you remember, in our bulbs, if we pull back our picture, and I'll just throw one up here that had the values listed on you, is that if I'm looking to be pulling from here the first time, the only way I don't get a first is I have to pull out of here. On the 10th pull, I've exhausted all of these because there's only 9 total. All right, so anything greater from 10, 11, 12, 13, 14, 15, you're guaranteed a 75 watt if you get to that number. Okay, and in fact, on the 10th pull, you're guaranteed 75 watt, and at the 10th, it's not even an issue because you've already pulled the 75. All right, so that's kind of a way of kind of looking at it. So it's kind of a trick that after number 9, we're guaranteed a 75 watt no matter what we do. All right, okay, now here's the problem, and I'll show you kind of the issue, is that to compute the number of ways this can occur becomes a little bit complex. All right, so let's just draw our pool picture for pulling it on the 6th. All right, I've got my sample space again, and we're doing 15 and 3. Okay, and so on exactly the 6th pull, what has happened is I'm looking for the probability of the event of having 1 on 6 and 5 on 9. Seems like what we were doing. Okay, now here's the trick. Okay, this might seem correct, but instead of calculating this, the sequence is going to start to matter, because what's happening is I meet the criteria when on the 6th pull I get what we would call a success, but all the ones prior to that are failures. Okay, so this problem is not a pool problem in this sense, all right? Okay, and so anytime we start talking about a sequence, we're going to go back to our product rule. We'll take advantage of that. Okay, and so here's what happens. Okay, let's set up our sequence, and I've written out all of them for the scenario. So let's take a look at the first one. The sequence for 6th pull being the success that satisfies all this is I have to fail the first 5. All right, so I fail the first one, fail the second, fail the third, fail the fourth, fail the 5th, and then on the 6th I get a success. That would be this scenario. Okay, now, again, we're going to assume without replacement, I'm not going to pull a bulb out and then put it back into the pool. Once it's out, it's permanently out. Okay, so the way I'm defining this is that failure is no 75 watt bulb. Okay, and then the success is a 75 watt bulb. So if this is my scenario using the product rule, I can go in and I can look at, well, what's the probability or the number of ways or probability that this can occur. All right, so if you look at it, we'll slide down here a little bit, that for the 6th pull, you can see the equation is on the very first, when you first start, there are 9 ways out of 15 that I don't get a 75 on the first pull, because there were 9 of the others. for the first event. For the second event, I failed the first one already, so now there's 8 on 14. All right, and then on the third, I failed the first two, so now there's 7 ways on 13 to fail, and 6 on 12, and 5 on 11, and so forth. Okay, and then this last one is where that first success hit. So this was a failure, that was a failure, that's a fail, that's a fail, that's a fail, and that's a success. So it becomes a sequence problem, if you will, in which we have, my first 75 watt on the 6th pull. Now, if we go back and we look at some of the others, you can see the chains all look very familiar, but you can see these chains start growing in length on this particular problem. All right, so for 7 pulls, it was, I had 6 failures and then a success. 8 pulls was 7 failures and a success, and I could repeat this process all the way down. Now, for example, I could come look at for the 7th pull, if you look, it's the same chain all the way out to my 5 on 11, but then I have a 4 on 10 multiplied in here, and then my success then is now going to be 6 on 9, because there's 9 bulbs there and 6 of them are 75 watt bulbs. So you can see this last guy here, those two guys start to change a little bit. Okay, but you can see this chain gets kind of long. It's not hard to compute this, but it does get long. What if you had 200 bulbs in the box? And I wanted to know the probability of at least, 190 this chain would be a mile long, all right? And so I'm not going to do the rest of them, but you can hopefully get the idea of 8 pulls, 9 pulls, 10 pulls, and so forth and so on, that I could finish this out that way. Okay, now, if you look at what happens is, when I wrote out the events, I did go into the chains, and to illustrate, at this point here, this was what I was saying was that after I get out to this line, which is the end of 9 pulls, if I have 9 failures in a row, everything after that is a success. So I'm really not even worried about what's happening from here to here, because all of these guys are guaranteed to be successes. Okay, all right. So now let's go through and let's try, well, what happens if I look at this in a different way? Okay, and so what I'm going to suggest is let's use the complement of our event D. So our event D was to have 6 or more, 6, 7, 8, 9, or 10. Well, if we take the complement of D, then it's not those cases. So I'm going to define event D as being that I get the 75 watt bulb on the first pull. 75 watt on the first pull. It's a success. All right, so, well, that's pretty easy, right? I could just go in and say, well, there's 6 of them, and there are 15 bulbs. It's 6 on 15, piece of cake. The second pull then is I fail the first, success on the second. Third is fail, fail, success, and so forth and so on all the way on. You notice that the chains are a whole lot shorter on this, okay? In fact, I can go through and I can calculate these complement events pretty easily. So D1's complement is the 75 watt on the first pull, right? So the term I'm calling D1, okay? The piece of the total is, so it's 6 on 15, okay? The second one, the pulling of 75 on the second, then is not 75 on the first and 75 on the second. It's now going to be 9 on 15 times 6 on 14 done. The chains are so much shorter on this. And then I can repeat the ideas down here. In fact, I wrote them out I just didn't write all the text for here. So it's 9 on 15, 8 on 14, 6 on 13, and so forth and so on. All right. So then the probability of the complement of the event that I want, which is basically just taking all of this and summing it up, is just simply the sum of all of those values, whatever numerically they are. And if you do the math on that, and like I say, I didn't write out the decimal values that come out of this. If I do the math, this complement event is 0.9580. It's 96% almost that I would get a 75 watt bulb somewhere in those first 5. But that's not the event as I defined it, okay? It is a much smaller problem, right? So once I do that, I can take advantage of one of those probability axioms that we said, in which, if you remember, we said probability of D plus the probability of not D was equal to the probability of the sample space. Okay, that came from our Venn diagram, right? That if I define that as D, then everything outside of this is D prime, right? And so region D plus region D prime is the combined sample space using our Venn diagram. Okay? All right, so what we have then is that if I rearrange this formula, the probability of my event D is just probability of the sample space minus the probability of that complement event, which was a lot easier to calculate, in this scenario. And we know the probability of the sample space is 1.0, and I subtract off that number I found, that 0.958. And so the probability of taking at least 6 to see the first 75 watt bulbs is 0.0420. It's about 4%. It'll take you at least 6 to see the first one, right? So that's kind of some strategy and some techniques that we can use to be able to work on that. All right, let's try one more for us. Okay, and so if we come in and we look at, and we've kind of hinted at this. So again, what you might want to do is I'll set up the problem, and then you can try to see if you can solve it on your own, and then re-engage the video, and then see if it works out. All right. So we're going to set ourselves up that we're looking at the probability of drawing 4 aces and 5 cards from a standard deck. So this is the old poker problem, right? Now, for those that aren't familiar with what we mean by a standard deck, it's a 52 card deck, 52 cards consisting of 4 suits, generally called diamonds, hearts, clubs, spades. And then within each one of these 4 suits, I get an ace, a 2, 3, 4, 5, 6, all the way out to 10, and then a jack, queen, king, okay, in each of the suits. Okay, and so there are 13 cards in each suit, and there are 4 suits. That's 52 cards. All right, so the number of ways that the number of outcomes that we're looking for for 5 cards is the number of ways of our sample space is being 52, 5 pulls on 52. So when I do that, there are 2,598,960 possible 5-hand decks or 5-card hands that come out of a standard deck of cards. And again, we're assuming that all the cards are uniquely printed. It's not a cheating deck. It doesn't include the jokers or anything else. It's just a standard fair playing deck, if you will. So about 2 million. And so now you can start to see, I wouldn't want to write out all of these 5-card combinations, right? You'd be here all weekend till next year writing all those things out. So we don't want to do it. So this is where these problems get big fast, right? And so you can start to kind of see. All right, so let's try using our pool approach on this. Okay, so if we come through and we do this, and this is one of the problems with the pool approach, is I have my sample space. Here's 52, I'm pulling 5, so that's the 52 on 5, or that 2 million number for this guy. Okay, and then out of each of these, the possible pulls that we could have then are, let's do aces, 2, 3, all the way out, and then king is the last one. So there's 4, 5, 6, everything in between. I just didn't write it out. Okay, and so to satisfy the problem statement, we said we wanted 4 aces, and there are only 4 aces, so you get all 4 of those. All right, so if I do this, the aces on this, I would have 4 on this one, and so the possible outcomes for that 5th card are, it could be a 2, it could be a 3, it could be a 4, it could be all the way down to a king that I'm pulling 1s out of. If I pull 1 out of 2, then everything else is 0. And you can see now I have 12 cases that show up, and this problem gets a little big and a little bit ugly. But you could go through and you could start to write this thing out and say, all right, let's do 4 on 4 and 4 on 1 and 4 on 0 and 4 on 0 all the way out to 4 on 0 at the king card, and that was my 2, that was my ace. You could write that and do the math on this. I mean, you could do the math on this thing. Okay, it turns out that the math's actually fairly easy on this one, but like I say, this is so long that it's just, and once you start getting that, you go, it's just not practical to do it that way. Okay, so it turns out that there are actually 12 different cases that can go with pulling the 4 aces, right? Because that's all that's left, or any of the 12 different suits, right? Okay, because again, I don't care what the ace is on those. Okay, now this is where the power of that binomial condensation starts to work out. Is let's recast this problem as, sample space 52 on 5. That's the same. I have an ace pool. Okay, 4 on 4. Okay, and then I have the not ace pool, because again, I don't care what the other card was. I wanted these 4. So it's that same idea, that same problem. And so we're going to do it with the complement. And so this A complement is basically, if this is an ace, then this is the not an ace, right? And so if I have 4 here, I have 48 here. And you'll notice in all of these pool problems that we've done, that the numbers that I'm kind of jotting down on the top as a reminder, that this plus this is that number. And it worked on all of the pools that we've done up to this point. So I'm going to do 4 on 4 and 1 on 48. And so this problem becomes very simple and very quick, that there are 48 hands that can show up where you get all 4 aces. And that should seem kind of logical, right? That one of every card left in the deck after you pull the 4 aces out. So there's 48 of those that can happen here. All right, so then what becomes is that the probability of getting 4 aces in 5 cards then is 48 divided by that 2,598,960. Okay, and so the probability of that is 0.00001847. You can see we're way down into the decimals on probabilities. In fact, this value corresponds to about 2 times in 100,000. You deal 100,000 5-card hands, and twice this will happen. Okay, roughly, not even, and that's not even guaranteed, as we'll talk about when we get into some probability definitions later on. But that's the general, all things being equal, this is kind of what we would expect to happen on this. So it's a microscopic number. All right, so if you ever get into playing stud poker on this, don't count on getting 4 aces. All right, and if you do, know that you probably can't beat that hand. Well, you can, but yeah. Anyway, let's not go to the casino anytime soon. What do you say? Okay, just those numbers are not worth playing the risk for. So anyway, that kind of concludes kind of some examples and kind of some techniques and strategies for how we can start to solve some of these permutation and combination problems. I like the pool approach, right? Because like I say, especially with this condensation trick that you saw here, that I can cast a large number of problems that we analyze in the real world into a binomial case, that it is one thing or it's not another. Okay, and then I don't get into the chaos that starts to come out of trying to resolve this whole thing. All right. So anyway, that's it for that particular video. I hope it makes sense and you kind of see some of the tricks and techniques that we use for doing this. Like I say, if you leave us some comments down below, as always, let us know what you thought, what your thoughts are, and what we can do better to improve your experience on this series. That would be greatly appreciated. And then, as always, toss us a thumbs up on the video and be sure to subscribe to the channel, and we will keep all of the content coming. So without further ado, I'll bid you all a wonderful evening. Happy engineering. Thanks.